Assalamualaikum and a very good day to everyone. My name is Nur Syafiqah binti Ahmad Zailani from Universiti Teknologi Shah. Today I'm going to present my study on electrochemical behavior of antimicrobial copper and its ion release in artificial sweat solution. This is the outline of my study and research. Before we go further, plenty of surfaces have been frequently touched by us on a daily basis. Hence, having copper that has been well known as antifungal, antibacterial, and antiviral agents can be very convenient for our daily hygiene. When copper goes through the oxidation process, which is from copper atom to copper 2 plus ion, it implicitly establishes its biocidal nature, which become toxic to microorganisms. Thus, may be benefits against pathogens such as Salmonella and E. coli. To cite Cassandra and colleagues, copper surface is proven to be 83 to 100% less bacteria contaminated than the conventional touch surface such as stainless steel. These few of the many reasons are why it is important to study its stability in the sweat solution. However, the problem is that as we want to commercialize copper as a touch surface, there is a possibility of tarnishing due to high amount of contact with human sweat. Thus, its corrosion resistance is to be studied along with its stability period, which equal to how long it sustains in the sweat solution. The significance of this study is that the relation between the electrochemical behavior of copper and its ion release in sweat solution will provide information regarding its stability as an antimicrobial touch surface. Hence, the scope of this study is to determine the corrosion rate of copper, to characterize copper surface before and after the immersion in artificial sweat solution, and to quantify the amount of copper ions released in the solution. Which brought us to the following objectives. First, to study the electrochemical performance of copper in artificial sweat solution using linear polarization resistor method, and characterize its surface morphology using field emission scanning electron microscopy. Second is to investigate the copper ions released in artificial sweat solution using atomic absorption spectroscopy. And lastly, to determine the relation between corrosion resistance of copper and its ion release with 3 immersion times. Now, we move on to the methodology of this study. The materials and chemicals used are copper coupons, which were polished using silica carbide paper and then cleaned in acetone. Next is the artificial sweat solution, which was made up of 0.5% of sodium chloride, 0.1% of lactic acid, and 0.1% of urea, and they were made for 100 ml before adjusting the pH to around 6.5. Instruments used were Autolab potentiostat model AUT302FRA2 interface with Nova software for alpha analysis. JSM 7600F model of FASM was used for the surface morphology. And lastly was flame atomic absorption spectroscopy used for copper ions release determination. The first part of this whole study was basically to determine the corrosion rate of copper after 3 immersion times in artificial sweat solutions using linear polarization resistance, also known as electrochemical test. Silver chloride was used as reference electrode with platinum rhode as control electrode, and our samples, copper coupons, as working electrode, while the glass cell contained artificial sweat solution as electrolyte. This test was ran on 3 copper samples that had been immersed in artificial sweat solution for 0 hours, which was as prepared, 1 hour, and 24 hours each. All samples were then covered to limit the surface area to 0.22 cm squared only. Second part was the characterization of copper surface before and after the immersion using FASM, which was done at 1000 times magnification and 5000 times magnification for better observation of the surface morphology. And lastly was quantifying the amount of copper ions released in the artificial sweat solution by standard calibration method of AAS. The analysis was run on 5 standard copper and 3 sample solutions that have been variably immersed with copper coupons. The 5 standard were prepared from 1000 mg per liter stock solution of copper, diluted to 10 mg per liter, which then diluted again to 0.3, 0.6, 0.9, 1.2, and 1.5 mg per liter of concentration. As we proceed to the electrochemical test results, the left-hand side showed the table plots of 3 parameters studied in this coursework. From the table above, 0 hour of immersion had the best corrosion rate, in which it only corrodes at 0.09412 mm per year, compared to 24 hours of immersion with 0.20534 mm per year. Lower corrosion rate also indicated higher polarization resistance, which we may deduce here that shorter immersion time means that the sample is more resistant to corrosion. Next is the characterization of copper surface under FASM visualization. 4 figures on the right show the surface morphology of 4 copper surfaces before and after immersion in the artificial sweat solution. Blank sample showed a smooth surface with polishing effect indicating it was 100% copper, while 0 hour sample showed no significant difference, which correlates with LPR data as there was not yet any reaction with the sweat solution. Hence, no deposition on the surface or no ions released. However, after 1 hour, copper surface has started to react with artificial sweat solution, and the deposited materials on both 1 hour and 24-hour sample will most likely come from the reaction with the solution. Therefore, longer immersion time showed a rougher uneven surface due to less resistance to corrosion. In any case, in order to determine what kind of material deposited on the surface, XRD or EDX analysis may be employed. Next analysis was to satisfy the second objective of this study by determining the concentration of copper in the artificial sweat solution, which regarded as unknown samples. And graph on the right is the standard calibration curve that serves as a reference based on their absorbance values. Meanwhile, the last figure on the left indicated immersion time is directly proportional to the concentration of copper ions released. For 1 hour and 24 hours of immersion, it again correlated with previous LPR data as in higher corrosion rate released more copper ions with 2.593 mg per liter and 4.814 mg per liter respectively, while 0 hour sample solution showed an acceptable result as the short contact time had released considerably few copper ions, which is 0.128 mg per liter. In conclusion, 0 hour immersion time of copper in the artificial sweat solution showed the best corrosion rate with 0.09412 mm per year, which also released the least copper ions with 0.128 mg per liter. At last, the third objective had been determined that corrosion resistance of copper significantly correlates to copper ions release, by which the longer its immersion time in the artificial sweat solution, the less resistant it is to it as it releases more ions. Certainly, the data of this study may contribute to the understanding of copper's compatibility with human sweat and facilitates the development of corrosion-resistant products for antimicrobial touch surface applications. These are some references I used in this study. And this is the end of my presentation. Thank you for your attention.